So I'm Han from University of Florida. Today I'm gonna present point-ahead angle mechanism stability tests for LISA at the University of Florida on behalf of our LISA group sitting right there. Okay, let's start it. Okay, so first of all, why do we need a PAM? Because due to the sheer size of LISA constellation, it takes the laser beam about 8.3 seconds to travel from one spacecraft to the other one. And I hope that this cartoon drawing on your lab is basically tells you why why we need a point-ahead angle. So there are actually two of them. One is the in-plane constellation. But for in-plane one, it's a fix, and it's caused by the constellation orbiting around the sun. So this point-ahead angle is fixed, a large, predictable, and a stable offset. But what makes the PAM mechanism useful is for dealing with the outer plane angle adjustment. So basically, the outer plane one is that the PAM would direct the beam, so that beam will catch up with the spacecraft in the future. There are some fun facts about the PAM. So first of all, most importantly, it's a step and stair operation. Step basically means it's not gonna adjust the angle continuously. It's gonna adjust the angle in one step, and once it got that to that angle, the control loop will keep the PAM fixed for the entire, for some duration of during the data collection process. And then, once it's done, it will move on to the next step. Okay. So, let's talk about PAM then. PAM, as we receive right now at the University of Florida, is engineering model 1, and I just call it PAM and EM1 interchangeably. So PAM definitely has to meet some key requirement. The piston stability requirement is actually more stringent compared to the requirement for other optical setup in the LISA instrument. It has to be 0.5 picometer per root hertz. And PAM is a mirror that's sitting nominally at 45 degrees of angle of the with respect to the incident beam. So it definitely requires additional angular stability, which is 10 nanoradians per root hertz. There are some other crucial requirements. We do concurrently have a setup that's going on, measuring the center of rotation of the PAM. That basically means the beam hitting the PAM has to be within 30 microns of the PAM center of rotation. And if you're really interested about that, please stop on Thursday at poster session and say hi to Jenny. She will be introducing her setup during the poster sessions. And also, we will be measuring these key requirements at 3 different offset angle, plus minus 300 microradians, and the nominal one at 0. Okay. So because PAM utilized piezo actuator to control the angle, so it would exhibit hysteresis and thermal drift over the time. So we need an ultra precise and non-contact capacitive sensors, basically to measure the angle and then control the PAM so that the mirror's angular displacement is stable. Capacitive sensors are really useful because they do not contribute to they do not introduce any shear forces that will destabilize the mirror and the spacecraft itself. Okay, so in general, how do we do the picometer stability test UF? The concept is very straightforward. So you have the test object, in this case, it's the PAM, and we form a cavity around it. We call it test cavity. And then you lock a laser to that test cavity, and then you beat it against a stabilized laser. In this case, the stabilized laser would be a laser PDH locked to a very stable reference cavity. And you form a B node between them, and you have the Phasemeter tracking the B node frequency offset all the time. And then you use this above formula to get the length displacement of the test object, okay? Assuming the frequency offset is much smaller than the 1060 nanometers laser frequency. On the bottom left, I show the CAD rendering of the PAM test cavity, where you have the input and end mirror of the cavities, and then the EM1, which is the PAM mirror, is sitting between them. Now, let's talk more about the test cavity we have here. So it's a very specialized cavity. Of course, it's a cavity, so it has to stay on resonant all the time. So we have to make sure it's geometrically stable. And then the first feature about this specialized cavity is the end mirror's center of curvature, COC2, is co-located with the center's rotation of the pen mirror. So this means that as long as the input beam is hitting dead on to the pen center's rotation, then the piston measurement will be immune to any angular noise. The second feature about the pen is, if I may you direct your attention to the plot, the drawing on the left, bottom left. So we can actually slide the pen parallel to its reflective flat surface, and then there will be offset between the cavity axis and the rotation axis of a pen, and this offset is recognized as the totaling coupling, TTL, and we can use this totaling coupling to project blank noise into angular noise. So these are the optical setup in air and in vacuum. So if you look at the top right pictures where we have the pen cavity, and then the EM1 is sitting at the center, the metallic one. And then we have a zero-dose standing cavity, which is almost identical to the pen cavity, except we replace the EM1 with a zero-dose standing in. And the zero-dose standing is basically a flat zero-dose mirror that takes expolization and it's mounted onto a zero-dose block. So all these in vacuum components, except for the EM1, was designed by our engineer, Joe Gleason. And then the schematic basically shows you the injection bench, which is responsible for injecting the pen laser into the cavity, create a PDH area signal so we can lock the laser to the cavity, and then forming a bead node. So bead it against with a pre-stabilized laser. So this is the actual setup. It's daunting. It looks daunting because it's more complicated than the drawing I show. So the red one is actually the input beam that goes into the cavity. It will hit the cavity mirror, bounce back, pretty much following the same path, but being rejected at the Faraday isolator, and following the green path, hitting the RPD, the reflection PD, where we generate the PDH signal. And the blue line is just a pick-off of the PEM laser before the EOM stage, before the PDH stage. And then it's gonna specially overlap with a pre-stabilized laser marked in cyan. And then all together, they will travel and meet the bead node PD, where we can measure the frequency offset of the bead node and convert that into the length noise. So these are nice pictures of a test facility. I do want to make several shout-outs right here. So if you look at the two pictures on the right, UF RPD, UF PDH servos. So these are UF made reflection PD and UF made PDH servo. They've been proven effective and working well with the previous STM testing campaign. And on the right, sorry, on your left, where we designed a UF super flange that was designed by our scientist, Dr. Alex Weaver. So on the super flange, it has a viewport, a flange that connects to the vacuum systems, sorry, the pumping system, and a D-sub flange that basically enable us to monitor the in-vacuum temperature and the temperature drift on the EM1 itself. And we do also have a number 4 flange, which has 4 SMA connectors. So these SMA connectors on the other end will be connected to the SRAM BB1M. This BB1M is the control modules that allow us to control the PEM. And the BB1M will be connected to the SRAM rack, which is basically a gigantic power supply. And we can control that power supply with an SRAM supply computer that has a specialized built-in program that we can just control the PEM pretty straightforward, easily. So last but not least, let's talk about reference system that I've been keep mentioning. So we do have 3 different reference systems in place. The anodyne one is more or less for longer term of measurements, and then another, like 2 reference cavity. Each reference cavity is sitting in 1 tank. So imagine when we have PEM being commissioned, we actually have 3 vacuum tanks working at the same time, and each vacuum tank has 1 cavity in there. And the plot on the left is basically the beat node formed between the two reference cavity, and then you can see basically the noise in our reference systems compared to the half picometer requirement, then PAN needs to be satisfied. Okay, so we do want to know how good our lab is. So we have this measurement to measure the noise in the environment. And how do we do this? This is quite simple. You just replace, no, not that simple actually. You just replace the EM1 with zero door standing and form a cavity around there, and you measure the stability piston noise, basically, of the zero door standing cavity, shown in blue. And then we measure different possible noise sources. And then as of right now, we do believe that if you look at the 2 millihertz corner on the blue trace, it is slightly above the requirement line. And we believe that because this cavity is RFM limited and also the cavity temperature limited. PAM is actually slightly different from the zero door standing because PAM is sitting on a 3 SIP feet. They can produce additional tilt that cannot be reproduced by our zero door standing. And we call this acceleration noise or gravity sag because we found that when we actually had the PAM cavity on resonance and we tilt the entire two-ton table, and we found that the B node actually shift by 4 megahertz when we tilt the table along the table's long axis. And this 4 megahertz beat node frequency shift actually allow us to estimate another kind of TTL introduced by the gravity sag that is not shown in the zero door standing in. And that number, TTL, is estimated to be 1 nanometers per milliradians. Of course, this is very rough, so we plan to measure this number more precisely later on. Okay, so this is the current stage, the PAM. So we try very different ways to try to improve the preliminary result of the EM1. Just notice that EM1 is not finalized, so we're still commissioning it. We're still trying to measure its true noise floor, and we just finished some injection bench overhaul, waiting on the inclinometer to arrive so we can monitor the sag. And okay, so here is the screenshot of the spatial model content of the zero door standing cavity. This is a victory within our own group. I do want to share this with the audience. And the final takeaway message will be, so verifying the stability of the LISA instruments on the ground is pretty challenging. But with the support from all our collaborators, our team at UF is making every effort to study the true performance of the PAM EM1. Thank you.
Thank you. Any questions for Han? There's a question online.
So the question is, what can be said about the PAM noise PSD below 1 times 10 to the negative 4 hertz?
I think this is just like an extension because we only need to meet the requirement between 0.1 millihertz and 1 hertz. So that extension, personally, I wouldn't even trust the line that is beyond the picometer requirement that is beyond, below the 0.1 millihertz, because honestly, we don't know that. And then I think our reference cavity, we need to bring the iodine laser back on, the iodine setup back on so we can measure the frequency ASD of the PAM at that low frequency.
Any other quick questions?
So perhaps you said this at the beginning, but is there like an effective arm length for the PAM, which is converting the PAM nominal rotation into a displacement?
Oh yeah, you mean angular rotations or?
Yeah, converting an angular rotation into a linear displacement.
Yes, that's exactly. So, okay, if you look at the orange and the blue there, right, on this preliminary results, so the huge difference, the difference that the blue is being improved is basically we make sure that the PAM is total length noise free, basically. So we measure we differ the PAM, and then we know how much the total coupling is coupled into the piston effect. And then when we show the blue curve, it's basically the total coupling is below some threshold. So it pretty much, the total coupling is 10 times less than the piston measurements.
Okay, and in terms of a length?
In terms of length, yes.
No, but how big is it in terms of lengths?
It's the total length that turns into the length noise is 10 times less than the length noise, if that's, or I can explain later if you.
I think in the interest of time, we should thank Han again, and maybe you can ask offline.
Yeah, thank you.
Thank you, Han. Okay, so we do have a couple of remote talks in this session. One of them is coming up now. This is Giulia Testa, and they're going to talk about a digital twin for the LISA GRS front-end electronics.
So good afternoon, everybody. Today I'm going to talk about the development and correlation of a LISA gravitational reference sensor front-end electronics digital twin, which is the topic of my master thesis at TTH Zurich. So first of all, I'd like to briefly go through the outline of this presentation. I'll introduce the topic of the LISA GRS front-end electronics, and then present our digital twin model and the first results we've obtained so far. And finally, I'll draw some conclusions. So first of all, what is the gravitational reference sensor? We've already had a great presentation this morning on this topic, but I'd like to give a brief recap to make sure that we're on the same page for the purposes of this talk. So the GRS consists of the test mass, which is the core of the inertial sensor of the gravitational wave detector for LISA, and all the surrounding hardware and electronics that control the test mass itself. The test mass allows to describe the presence of gravitational waves since it is in pure geodesic motion, and the GRS hardware ensures that the test mass is actually in free fall, and it limits all external and internal force disturbances that may affect it. The test mass is a cube that is surrounded by an electrode housing that includes 18 electrodes, and are used both for the capacitive sensing and for the electrostatic actuation on the mass. In case of movement of the test mass from its reference sensor center position, the GRS front-end electronics measures this displacement via an AC excited capacitance bridge. Essentially, a displacement of the test mass causes an imbalance between the electrodes and the test mass, and therefore an imbalance in the sensing bridge and the currents that flow through it. And this generates a differential signal that is then amplified and filtered. The output voltage that we get is proportional to the differential capacitance between the electrodes and the test mass. And through the linear combination of the total 6 channels, we get information on the 6 degrees of freedom of the test mass, the 3 translational and 3 rotational, and this allows to perform electrostatic actuation on those same degrees of freedom through the drag-free altitude control system. Now, to have a digital twin for this whole system would be not only interesting, but possibly also very useful, because it would mean to have a platform that reproduces the system dynamics, and depending also on the level of detail, we would be able to study how the system responds when affected by different noise contributions, for example, or even in case of changing conditions during the mission, such as temperature fluctuations. And the goal would be to have a parametric model correlated with on-ground measurements in order to obtain a detailed representation of how the real experiment behaves. We thus come to our work. We've so far developed 2 separate simulations, one for the sensing and one for the actuation chain. They're both based on Simulink, which is a graphical programming environment based on MATLAB. And the general scheme that we follow is to define the inputs in MATLAB, send them to Simulink, run the simulation, and finally analyze the outputs in MATLAB again. We can now take a closer look at how the simulation schemes look like, starting from the sensing one. We've implemented the different stages that constitute the sensing chain, starting from the sensing bridge, with here highlighted in red the capacitances that represent the capacitances between the electrodes and the test mass that I've previously mentioned. Then we have the preamplifier stage with the transimpedance and differential amplifiers. Following this, the bandpass filter and the demodulator stage. As I already mentioned, we have input MATLAB scripts to define the parameters for the different elements that appear in the electronic chain, and also MATLAB scripts to generate noise time series that we can inject at the different stages if wanted. Once the signal is generated and processed, we get the output to MATLAB and we can analyze it. What concerns the actuation simulation, we're currently interested in reproducing the generation of waveforms and trying to understand how these actuation commands are affected by noise. So we're focusing in particular at this stage of the actuation chain and considering how the actuation commands are defined for the 12 actuation electrodes, which are the green ones in this picture. We have these 3 different contributions, which are 2 sinusoidal terms and 1 DC term. And therefore, the very basic image of our actuation simulation looks like this. We have these 3 contributions, they're generated, combined, and we get the output for the analysis. Actually, we also have an intermediate stage where we've reproduced the quantization according to the FPGA processing and according to the specifics of the onboard computer and the front-end electronics. Here I've listed just some of them. At the last stage, we can also mix the clean signal with noise and see how the simulation responds. We now come to our first results. For what concerns the sensing simulation, we've first of all extracted what are the gains of the individual stages that constitute the sensing chain. We've compared them with the values that are expected when considering the nominal values that appear in the electronics, and in particular when considering 0.12 picofarad for the differential capacitance between the electrodes and the test mass, since this is the measurement range of the high resolution mode. Here we can see the simulation extracted values and the relative errors. They're all quite in good agreement with what we would have expected. And for the further analysis of particular interest is the result in the second to last row, which is the total sensing gain. And this is the gain needed to extract from the output voltage what was the differential capacitance that generated it. And to test how good our value that we extracted actually is, we performed the simulations with different input differential capacitance values and extracted the slope of the curve that these values make with the output voltage. In this table, we can see the results of the linear fit. And as you can see, they are in very good agreement with the values that we extracted from the simulation of 0.12 picofarads. And therefore, we can confidently use these values for further analysis. What we did after this is to inject different noise sources into the simulation. We considered the test mass injection noise and the temperature noise that affects both in simulations that affect both individually and simultaneously the interested stages, which are the transimpedance amplifier, the differential amplifier, the bandpass filter, and the demodulator. We can see the results in this plot. So I'm showing the different simulation cases when taking into account only the test mass injection noise or the temperature noise individually injected at the stages or simultaneously through the 4 of them. On the y-axis, we have the residual differential capacitance with respect to the reference value of 0.12 picofarad. That is the value that we considered. And in all of these cases, you can see that our results are within a 95% confidence interval with the expected value. And this suggests that our simulation actually responds pretty well when injected with noise, and you can still extract the correct differential capacitance. This is what a time series looks like when we inject the simulation with temperature noise. Here I'm showing the simulations where the temperature noise affects the individual stages and also the 4 stages simultaneously with the blue data here. And the model that we considered is given by this power spectral density that we have above. That was extracted from the LISA Pathfinder campaign and adapted in this model for the LISA mission. This same time series in the frequency domain look like this. These are the amplitude spectral densities in the 5 cases that we are considering for the temperature noise. And in particular, we can focus on the blue data, which is the case when the temperature noise was injected at all the stages. And as you can see, the simulation data are in very good agreement with the model that is represented by this red line. We're currently performing longer simulations in order to explore also lower frequencies. And this is a first example that I can show you. And you can see that also at lower frequencies, the simulation data follow the behavior that we would expect. We can now turn to the actuation performance. And first of all, we can take a look at some outputs of examples of simulations when considering different electrodes, one of the 12, and the correspondent frequencies, and choosing some amplitudes for the actuation comments. This is the first example. Then we considered another electrode with different amplitudes and a third one. In all of these cases, we can see that the data, which are represented by these blue dots, are in very good agreement with the expected behavior, and also the frequencies extracted from the amplitude spectral density study are in complete agreement with what we were considering for the specific cases. These examples account from simulations where we did not inject noise. When considering noise instead, we considered this expression. V of t represents the clean signal to which we combined a correlated, uncorrelated, and additive noise contributions. This is what the amplitude spectral densities look like in this case when injecting all these 3 noise contributions to the simulation. On the left-hand side, we have the plot of the total output. So we have very strong resonances at the frequencies that we were considering for the specific comments. And down here, the shape of the noise. We've isolated the noise on the right-hand side. And as you can see, it again follows very well the model given by the red line, model that is actually dominated by the additive noise contribution and that therefore looks pretty flat for this reason. We thus come to the conclusions. We've presented the first attempt of digital twin for the GRS front-end electronics on Simulink. This is a very flexible platform that allows a very detailed representation of what we want to recreate. We've investigated how different noise contributions affect the system and how the simulation responds. And our next steps will be to perform calibrations and correlation of the model with on-ground measurements in order to obtain a more accurate representation of how the real system performs. And possibly this will become an important support for both on-ground and in-flight operations. Thank you.
Thank you, Giulia. Do we have any questions for her?
Thanks for the talk. Maybe a very quick one. I agree that for supporting when Lisa will be or when you will build the front-end electronics is important. But you showed just comparison between your modeling and what you put as a model in your simulation. Have you tried to test this with the data from Lisa Pathfinder, for example, I don't know, to see if it matched? We did this in Lisa Pathfinder, but with the one that you built. Yeah, thanks.
No, thank you very much for the suggestion. Actually, we've not yet done this, and certainly it will be a very useful tool to compare both with the Lisa Pathfinder's data as well as the on-ground measurements for Lisa, and for sure we will do that in the future. Thank you.
Thank you. Any other questions from the room? We don't have any online at the moment. Giulia, let me ask you a quick question. Does your model handle crosstalk or cross-coupling between the degrees of freedom?
Not yet. The plan is to implement it in the next few months, hopefully during my thesis, but we'll see what we can do. Yes, for sure. The goal is to be as to have the best representation that we can get of the real system, so that also will need to be implemented.
Okay, Thanks, Giulia. Let's thank the speaker again. And now we have Wolfgang Kastaun.
Yes, can you hear me well?
Yes, we hear you just fine. Wolfgang is going to tell us about the LISA instrument simulator development for Mojito.
So I'm afraid this is not a talk about hardware, but just software. So what is LISA instrument? That is the DDPC high-level instrument simulator. It is an open source package, and you can find it in these repositories. It's also available on PyP, can be easily installed with pip install, and there's also an online manual. I assume the slides will be distributed, so you don't have to copy those links down. Some features, it generates simplified L0.5 data. Simplified means there are no auxiliary channels like temperature sensor or something, but all the interferometric signals are basically simulated. It works in the time domain. You can inject arbitrary gravitational wave signals. You can use realistic orbits. You can activate laser locking together with frequency plans, and you can inject glitches into various components. Most importantly, it generates noises for various subcomponents on a very high level. So it's not simulating those subcomponents, but just assuming some PSD model and then inject the corresponding noise. This package lives in a larger ecosystem of codes. The green boxes here are codes. So there is LISA orbits, which basically extracts the spacecraft separation from the ESA-generated orbital position files. There is LISA GW response, which creates the arm length change from strain data of gravitational waves. There is LISA glitch, which generates a file with all these glitch injections I was mentioning. And then downstream, once you have the L05 data, you can input that in something called lollipops, which performs TDI analysis and generates L1 data. What is this currently used for? It's mainly for generating common data sets. So I'm not going into the details here because there will be a whole talk about that by Jonathan Menu. I just want to mention that for the generation of these common data sets, you need to simulate 2 entire years. And the LISA instrument code is used to generate the noises, not the GW, not the gravitational wave signal, just the noise. Now I want to talk a little bit about the recent developments. Recent means during the last 2 years or so. First, we had to do a complete internal refactoring. And in this process, we added quite a bit of infrastructure. So there is chunked processing. There is a signal processing with interpolation and filtering. There are some noise definitions and noise generation modules. And then we improved the noise modeling. So there are, for example, some unintended non-stationarities in the older version, which are now gone. And then we have started to include non-stationary tilt-to-length coupling coefficients. Recently, we added reciprocal backlink noise. So these 2 motors are connected by a fiber, and this can generate some noise that is the same for on both sides. And currently, we are also working on making the shot noise dependent on the arm length via physically correct formulas. The user interface changes were intentionally kept relatively minimal. However, there are some, when writing new code, there are some new possibilities. So first of all, the results in L0.5 files are now on equal footing with results you generate on the fly into memory. So you can write code that works with both quite easily. And we also made a bit more clear what is metadata and what is kernel attributes of these instrument code. So this is all a bit cleaned up. Let me talk a little bit about chunked processing. So the motivation for the refactoring and this chunked processing was that we simply could not generate 2-year simulations because it had to fit all into memory in the old version. And this is just requiring too large RAM. So we developed a custom streaming framework where you basically have objects we call streams, and you can connect them in various ways. For example, you can form arithmetic expressions of those. You can, if one of these streams represents a time, you can input it into a function to sample this. There is a noise generation stream. Then you can apply delay operations, either fixed or dynamical, by when the delay is given by yet another stream. There are filter operations, infinite response and finite impulse response, time integration, differentiation, downsampling, and very importantly, you can then connect the stream to an HDF data set in an HDF5 file or to a NumPy array if you want to store results in memory. So this allows quite efficient evaluation. So the memory usage is now pretty low. And most importantly, it's independent of the simulation length because it's now all evaluated in little chunks. So basically the time series are chopped up and then everything is basically flowing from one end of the stream, the source, to some destination like a file, and you don't have to keep everything in memory. And the upshot of this is that you can now generate 2-year data without problems on a typical laptop within hours, or let's say overnight. Depends also how fast your hard drive is. We also did some optimizations like propagation of constant mass, but I'm not going into details here. Then we improved a little bit the noise generation. So that wasn't a purely technical problem. For most PSD requirements, the PSD curves are of course only supposed to be met within a certain band. But if you actually want to generate noise, you need the PSD down in principle to 0 frequency. And if you just take one of these formulas that are in principle valid only within a band and take them down to 0, many of these formulas have something like 1 over f to some power. And this is the divergence and not a valid PSD. And if you actually try to generate such noise, you get non-stationarities. That was actually a bit of a problem, but we have solved that by introducing parameter, and below this cutoff frequency, how we call it, we just replace this idealized model that is not even valid there by a flat curve. And we also had to tweak the technical implementation of the noise generator to allow something like that. And this worked rather well, so we can now generate all the noises perfectly stationary. In particular, test mass and laser noise were affected by this non-stationarity problem, and this works now just fine. In principle, we also would need the noise PSDs above the measurement band because we generate noise internally at 16 Hertz. And we are supposed to also modeling things like aliasing. And in principle, we are also making implicit assumption what goes on at higher frequency. So there's still room for improvement. Let's come to some open questions. One is the handling of orbital data and in-band artifacts contained therein. Then we are investigating some numerical precision issues. And as always, the file format is an endless story. Finally, there is also another simulator from performance and optimizations, which has a bit of a different focus, but we try to make some comparisons. So let's talk a bit about orbit data artifacts. The time derivative of light travel time enters the response pretty directly via Doppler shifts. And therefore, you need to avoid any unphysical in-band contributions of numerical errors in the orbit data. However, if you compute orbits, you typically focus on getting very accurate positions, and you don't really think about this in frequency space. So we don't need that accurate positions. What we need is that the in-band fluctuations, so fluctuations with a frequency between 10 to the minus 4 and 1 Hertz, they need to be very small. And that are two different things. So the ODE solver that ESA provided offers very limited control over this in-band error. And what we currently do is we solve the ODE with a very low sample rate and then use upsampling. So there's quite a frequency range involved. The orbit is on time scales of years, whereas, or let's say the physical effects are on time scales of months, whereas we need at 16 Hertz basically the orbit data. Now, it makes quite a difference how exactly you do this upsampling. So we are currently investigating also an explicit bandpass filtering before the upsampling. And I'm not going into the details here, but just below you see two different ways of doing just the upsampling without any filtering yet. And the blue curve and the black curve differ quite a lot. And you see basically this red area that is both within the measurement band and above the noise requirement. The blue curve is sort of entering that, which is not good. So one has to be a bit careful, and that's something we are currently investigating. Another issue is numerical precision. So I'm talking about the finite number of digits that you can store in floating point numbers. So we are currently using double precision floating points, and we're also doing something where we split the small fast fluctuations from slowly varying large offsets. But despite all these splitting, we still have some cancellation errors, which are unavoidable, which reduce a little bit the amount of valid digits. And this seems to affect the upper sideband simulation in a way that can become relevant for some post-processing steps, like some ranging, fitting. And we might need to use extended precision. That has already been necessary in this lollipops code I mentioned when converting TDI variables, just for the internal computations. So yeah, this might become necessary for art as well. Finally, future developments. We want to phase out the current user interface, which is a monolithic, historically grown abomination with hundreds of parameters. Not hundreds, let's say around 100. There's the idea to make a more cleaner, modular system that is friendly to configuration management if you do simulation campaigns. Then on the physics side, we need to include control loops, so the dynamics. And this will require quite a bit of development because there's some qualitatively different in the terms of how stuff depends on other stuff than now. So this will be some work. Easier is more realistic modeling of onboard anti-aliasing filtering. This is mainly not done yet because the actual hardware design is not finalized either. Then it would be good if we make the noise modeling more flexible, so you have more choices, and we want to synchronize to the performance budget at one hand, and possibly any results from hardware modeling and or testing. Finally, as a sort of bonus for users, I mentioned this streaming infrastructure we use internally, but this could also be very useful for post-processing and data analysis because also there you might run into memory problems. And it's basically very usable, but the documentation is a bit sparse. So basically I will make better documentation and then this can also be used. Okay, with that, I'm done. I hope I was in time. Questions?
Thank you, Wolfgang. We are running a little bit over, but are there any quick questions for Wolfgang? I would just ask quickly, how often do the new releases of the instrument simulator come out? And is there a release process?
Well, there are no regular releases. This is mainly driven by demand. For example, just recently we released something because it was needed downstream in the L01 processing. But right now, where this Mojito data set is basically in full swing, we have releases every few weeks. In the near future, probably even more often. Between those common data set generation, it might be a bit slower release cycle, but yeah, it really depends on demand. So if anyone urgently needs some feature or anything, we are very open to creating another release.
Okay, let's thank Wolfgang again. Next up, we have Peter Wass from the University of Florida, and he's going to talk about the Gratis project.
I'm here to talk about the simplified gravitational reference sensor for Earth geodesy applications. So a bit of a change from LISA, but hopefully there's some synergy here. So yes, ultra-precise accelerometers and gravitational reference sensors, if you like, are used in a lot of different missions in space. So we have applications for Earth geodesy on the Giulia and Grace follow-on missions. We have applications in fundamental physics, in microscope and gravity probe B here. And also, of course, LISA and LISA Pathfinder for the detection of gravitational waves. So why do we want to build or design another one of these? So when you look at the acceleration sensitivity of some of these instruments, you can see there's quite a big gap between the performance we achieved in LISA Pathfinder and the kind of instruments we have in Earth orbit for geodesy and fundamental physics applications. So we see between 10 to the minus 12 and kind of 10 to the minus 15 range, there were no instruments in that gap. And so back in 2019, we were awarded a grant by the Earth Science Technology Office at NASA to develop an instrument which would leverage LISA Pathfinder technology to kind of improve on the state-of-the-art performance and bridge this gap a little bit. While at the same time, because we're not aiming for LISA Pathfinder performance, we think we can reduce the size, weight, and complexity of the instrument. And so initially, this was targeted at Earth geodesy applications. And so the design drivers we had were kind of driven by the Grace follow-on mission. We wanted capacitive sensing of the test mass at around 1 nanometer per root hertz to match the satellite-to-satellite tracking performance. We want accelerometry measurement with picometer per root hertz sensitivity. And we want to be able to operate in low Earth orbit drag conditions. And that's kind of sets our dynamic range, how hard we can push the test mass to hold it still as an accelerometer. And we want to be able to operate around 500 kilometers where Grace is. So together with our partners in industry, BAE Systems, we came up with this concept for the simplified gravitational reference sensor. We have a 30 millimeter cube, it's half a kilogram, made out of tungsten. We have gaps around the test mass between the electrodes of about 600 microns. And we utilize UV discharge to maintain the test mass charge under control. So that lives inside this assembly that looks a little bit like a LISA GRS, but we do not have, for example, a vacuum chamber because we have relaxed performance requirements. We tried to simplify the caging mechanism using a single finger instead of this 5-finger system in LISA. One thing we did include is a magnetic shield to relax the requirements on the spacecraft platform for magnetics. And then we have 2 electronics units which control and make the measurements. We have a precision box which has the capacitive sensing and actuation, and then a power supply and caging control system. So how does this perform? If we can break it down into the noise budget on a conventional platform without drag-free micropropulsion, we are limited by the actuation voltages we need to apply to the test mass, an accelerometer, and of course the capacitive readout. But if we went to a drag-free platform using microthrusters, then unlike those missions that we've seen before from Gauche and Microscope, we're not limited by the grounding wire that's included in there, so we can push the noise floor down to below 10 to the minus 12 meters per second squared, and then we're limited by Brownian noise around the test mass. And if we were to push the complexity a little bit and improve the vacuum in there, then there's nothing to stop us reaching below 10 to the minus 13 meters per second squared per root hertz. Of course, once you're at this level, you're completely dominated by the readout noise, and so you would need, to be able to exploit the full performance, you would need an improved optical readout. So for example, something like a picometer per root hertz would give you a much broader band. So where does that look like compared to those other missions? We can place the accelerometer mode curve here, just sits right alongside these other missions. That's kind of the goal, to produce something of comparable performance. And then on the more high fidelity instrument, we're pushing within sort of an order of magnitude of the LISA Pathfinder performance. And so we wanted to not just design and test this, but fly it in space. And so in 2023, we were awarded, again by ESTO, an INVEST proposal to fly this SGRS. And the aim of this gratis mission, that's Gravitational Reference Advanced Test in Space, Advanced Technology Test in Space, sorry. The aim is to demonstrate and measure the noise floor of the SGRS instrument, but also to establish the feasibility of using a low-cost commercial spacecraft for precision measurements in space. And so the launch of this mission, very ambitiously, is in February next year. And so we're working very hard to achieve that right now. And so this is what it looks like in the kind of CAD rendering. So we have two SGRSs on board. And we use combine the measurements from the two of these to establish the differential noise floor. We package that all up with its associated electronics, attach it to a base plate, and then that fastens onto our spacecraft. It looks a little bit like this from Apex Space in California. For scale, this is kind of a little over a meter long and a little under a meter wide. And the total mass of the spacecraft is going to be around 235 kilograms. So it's much more than a CubeSat. It's really a capable platform that we can use to make some serious measurements. Also included on board is a secondary payload, Odin. And if you're interested to hear more, then Felipe has a poster. You can go and see about that. That basically sits on top of our deck here. So if we're launching in February, we better have some hardware to show. And so here's a TRL-6 model that we made of the sensor head. So this was basically built to show that the test mass could be held against vibration loads without failure. So that test passed. And right now we're building the flight version of this. The caging mechanism's there on the right and the test mass. We also have a prototype setup of the electronics on the bench in the lab at UF. That includes capacitive sensing, actuation, and UV LED-based discharge. We've used that to make measurements in the lab. So on the top here, you can see that we can pulse the UV LEDs the same way we do with the LISA charge management. We synchronize that with the AC injection voltages for the SGRS. And we measure the phase stability there, and that's within requirements. On the bottom here, we are measuring, bottom left, we're measuring the actuation stability of the sensor voltages. That's really the critical performance driver for the accelerometer. And we're able to do better than 10 parts per million with an actuation of 80 volts. And then the capacitive sensing is also working to specification around a nanometer per root hertz. One new thing for Gratis I mentioned is this magnetic shield that was not included in LISA Pathfinder. But here we built this mu metal shield to enclose the test mass to shield it from the rest of the spacecraft and the Earth's magnetic field. And we're able to demonstrate suppression of the magnetic field by more than a factor of 40 at the test mass, which is sufficient. And we were able to vibrate this magnetic shield and show that it had no degradation in performance after vibration. We also have a prototype of this sensor head. This isn't the flight sensor head, but it's a replica. And we have that mounted on a micro-precision stage in a vacuum chamber. We're able to operate that in closed-loop control to simulate the motion and control loops of the SGRS. We have an independent laser interferometer readout and an isolated test mass to demonstrate discharging. So over in California, meanwhile, our spacecraft is nearly ready for us. So this is our spacecraft that will be used for Gratis, and this was on the vibration table last week, doing some workmanship vibration. So finally, once we're up in orbit, we want to be able to demonstrate the noise floor of this instrument, but we do have two things to contend with. We have the drag acting on the spacecraft, so it's simple enough to subtract the common mode drag from the two SGRS. But we also have rotation of the spacecraft, which induces Euler and centripetal accelerations. And to subtract those off, we need to be able to measure the angular rotation of the spacecraft and to be able to know the separation of the two SGRSs very well. So we do that precisely on ground, first of all, and then we use the combination of the star trackers on the spacecraft and the SGRS angular readout to back out the angular rotation of the spacecraft. We're able to do that, at least in simulation. So our simulations are showing that the centripetal and Euler contributions are subdominant, and we should be, at least in some cases, dominated by the actuation noise of the instrument. So I mentioned that this mission was targeted at Earth geodesy at first, and so that's definitely an application for this technology. You could use it as a simple accelerometer to measure the drag on a mission like Grace, to counteract, to compensate for non-gravitational forces. You could also use it as a drag-free reference on a similar mission. And then that could be used either on like a high-fidelity Grace successor, so a big mission like Grace, or a possible constellation of smaller spacecraft with slightly reduced performance that can do the same thing. And if you'd like to know more, I think David Weiss has a plenary talk on Thursday morning. We'll talk about this a little bit more. It's also possible to use SGRS or a pair of SGRSs as a gravity gradiometer. And so that's another possible application. You could use this either to measure Earth's gravity gradient or other planetary environments, possibly. There's a proposal to use a sensitive accelerometer like the SGRS for the Earth energy imbalance measurement. That's basically measuring the difference in the radiation pressure coming from the Earth out and coming from the sun in. And if you track that over time, you can see the effects of global warming, basically. You see that net imbalance is driving global warming eventually. And there's also a proposal from Jake here to use something like SGRS possibly as a decihertz gravitational wave, in a decihertz gravitational wave observatory, focusing on a kind of low-cost measurement of discovery type mission. Okay, that's about all I have. So just to leave you with a photograph of the team and our spacecraft here sticking up in the background. Thank you.
Thank you, Peter. Questions?
Maybe a couple of questions about the motivation, actually. So one is the like Grace fall on and things like that. But when you comment on the fact, I heard about that the main problem for now is the ability or the precision in the modeling of the signal, and not much the noise that the level. So if you improve the GRS, I mean, what is the advantage of that? That's the first question. Maybe I have one of this year's, but you want me now or?
I can answer your first question.
Yeah.
Yeah. So yeah, so you're right, the accelerometer is not limiting the main grace measurement right now, but there are conceivably ways that you could use an improved accelerometer to analyze the data in a different way to improve the data. A second answer to that is if you had more than one spacecraft, or more than one spacecraft pair. So that's the aim of doing this cheaply, but on a bigger scale. So you could have a constellation of spacecraft that defeat the aliasing problem in GRACE. Yeah. You can ask Jake about the decihertz.
Yes, we are running a little bit behind. No.
I'll cut to the chase. What limits the capacitive sensing? I saw it was at like the little bit more than a nanometer level. I thought with the slightly smaller gaps, you might be able to do a bit better, but just curious.
The actuation voltage leaking through the filter, through the bandpass filter, and then the gain.
Yeah? Okay, very last one. Jake.
So for your noise estimation in flight, you're talking about differencing the test masses in order to get the drag. How much is that limited by the strong actuation since you're in accelerometer mode, the noise on the very high actuation that you said you need? That doesn't limit it?
That's the limit we're trying to find.
Okay.
That's the limit you would find, yeah. Right. We would get, by doing the subtraction, we get to the noise floor, which would be dominated by the actuation. Yeah. Yeah.
Okay, let's thank the speaker again. Okay, next up we have Juan Jose Esteban Delgado. He's going to talk about verification of the LISA Phasemeter.
Yeah, my name is Esteban. I'm working for the Max Planck Institute for Gravitational Physics, Albert Einstein Institute in Hanover, Germany. Talking about the electrical verification of the LISA Phasemeter. I'm able to, okay, oops. What happened here? Let me first just put in context the LISA Phasemeter inside the LISA spacecraft. So basically the spacecraft is classically divided between the platform and the payload here. So from the payload basically, so there are three big systems. That is the optical metrology system, the gravitational reference sensors, and the diagnostic system. So from the payload, so basically you have the optical metrology system that consists on the telescope, the laser system, and two big assemblies that are the optomechanical chain and the SDPC, the signal detection and processing chain. The optomechanical chain, it's basically consisting on the optical bench with the hosted unit that are the mechanisms, the point-ahead actuator, the beam alignment mechanisms, and the fiber switching section controlled by the OBMCU, that is the electronic box that actuates over the mechanisms, and then the optical bench. The interface between the OMC and the SDPC are from the QPR here that convert the optical lights into the voltage. And this is part of the SDPC group. The SDPC is composed by the 8 QPRs that read the optical bench and the Phasemeter. The Phasemeter basically consists of two units, the interferometric processor unit, the IPU, that is the core of the Phasemeter, and the PCU that is like the computer of the PMS. The voltage are processed by the IPU, transferred to the data management unit, the PCU, and the information from the payload transferred to the platform. I can change the, okay, here. So the implementation of the SDPC, or this architecture and the verification process, is coming basically from this, explained from this diagram from here. So first of all, thanks to the funding agencies that are basically ESA, of course, the Federal Ministry of Research, Technologies and Space, and funded through the German Aerospace Center. ESA is the OMS lead. AI is responsible of the scientific SDPC aspect, with a contract, industrial contract for the BMS implementation via OHB, and OHB is responsible of the implementation of the IPU unit, and subcontracting DSI for the PCU, funded by ESA. So from this diagram, you can see the different verification process where the industrial contractor DSI will verify the PCU standalone. OHB will build and verify the IPU standalone. Then the electrical verification, it's coming in the integration level here at OHB premises. And then the further integration to the QPRs or to the spacecraft are coming to higher level verification process. If you have more interest on the optical verification process, so I encourage the audience to attend to the presentation from Ada on the end-to-end payload verification, or the SDPC conducted by Lea, or the other research activities by Live or Alvise on the optical platform that we are using as well for the verification of the instrument. Why is not? Okay. It's not. Okay. So if we see, I'm very sorry for the transitions. If we look into more details on the Phasemeter, basically is what you can see here. So the Phasemeter, composed by the two units, is also following a modular architectural design. The IPU consists of 4 backend electronics that are reading the photoreceiver signals from the QPRs, and one middle module that is the frequency distribution that is synchronizing the 4 backend electronics. If we see the functions of the IPU, basically the first is the signal conditioning from the QPR voltage to the dynamical range of the ADCs. This is one of the most sensitive part of the Phasemeter, and it's basically the analog electronics that is required for the digitalization of the signal. On the IPU, it's the function of the interferometric readout, the longitudinal and the angular displacement. The FFT, so the IPU, behaves as a spectrum analyzer as well for the big note acquisition process and the modulating the signals on the optical link, like the clock side bumps and the pseudo ranges estimate and the optical data communication as needed for the TDI functions. So the IPU is basically computing or reading out the raw data per QPR. The PCU is responsible of building the interferometer level observables from the QPR's readouts. So this is a task of the PCU as well as the transition of the different modes and the laser transponder implementation. All this information transferred to the platform. If you have more interest on the inside of the Phasemeter, I encourage you to go to the poster session and see the Mauritius and Miles Clark presentations here. So the IPU is the most sensitive and scientifically driven part of the Phasemeter. That was subject of the technology development for mission adoption, and we upgraded in this process from TRL4 to TRL6 instruments. So here you can see some of the technical requirements for the IPU, like the number of channels, the longitudinal displacement, the angular displacement, the pseudo ranges estimates. And here you can see some of the results obtained during this phase. A TRL6 demonstrator where the optical displacement is achieved, as well as the angular readout noise, the timing stability of the instrument, or the synthesis of the gigahertz clock side bumps. So our target now is to industrialize the instrument, moving from TRL6 to EM, QM, and FM. Here is the overview of the test setup for the electrical verification. So that will happen at OHB premises. So basically, it's a digital signal synthesizer that we call OVA simulator, that it's a digital instrument capable of producing up to 32 channels, independent channels, that mock up the behavior of the different interferometer on the optical bench, like the sign IFO, the test mass, or the referent. It's possible with this instrument to synthesize the different correlated and non-correlated noise, like laser frequency noise, like ring, like shot noise. And those are the stimulus for the device and the test that are the IPU and the PCU. You can see a hardware realization of one of the pre-development just to validate the performance of the OVA simulator on this photograph from here, the BMS on the baseline design, and all computed by a ESA instrument that is the onboard computer. This is basically the setup for the electrical verification. So, but this electrical verification has several limitations in the representativeness of the instrument. Basically, the electrical simulator of this verification process is very deterministic. So we can only synthesize noise levels and signal levels predictable as our best understanding of the performance models. So it's not fully representative of other noise sources like it could happen on the optical bench, like a stray light or microvibration effects and so on. So it's a very deterministic way forward for the acceptance of the BMS from the industrial contractor. So basically the target of this electrical verification is the validation of the interfaces, the verification of design functions, operations, data transfer, signal processing chain, and based on some pre-configured noise sources and signal levels. What is not representative is because we are not basically testing real physical signals, like, for example, as I mentioned, ghost beams on the optical bench or whatever unknown behavior when the different subsystems are integrated together. So, and it is not representing some spacecraft level closed loop operation like DFAS or constellation acquisition process. So basically the electrical verification, it's a pre-programmed stimulus for the verification of the PMS and has another, let's say, caveat that need to be mentioned. So all the electrical verification platform is synchronized to the same clock sources. So what it means is that the dynamics of the signals are pre-programmed inside digital logic to make the ramps or the Doppler fluctuations, for example, but everything based on one single clock. So to have unsynchronized Phasemeter as expected for the TDI calculations in the clock noise removal or laser frequency noise, so this instrument needs to go to higher level integration facilities like the Hexagon experiment on the SDPC level, or with the integration of more representative subsystems like the end-to-end test at Kennes in France, or for DFAX verification together with ESA on the avionics test bench. So basically, as conclusion, so the instrument is in an industrialization process, moving from the TRL6 to the EM, QM, and FM levels. This electrical verification is an acceptance industrial activity to move to further higher level verification steps, but it's the only one that it's testing the full chain, EM, QM, and FM, because Hexagon and Kennes, they are going to just to test on the EM and the QM, basically. This is the main benefit. So thank you very much.
Yes, thank you. Do we have questions here?
So Esteban, thanks for the talk. You mentioned ghost beams, but I was curious, with the Phasemeter, are we at all worried about like some spurious tone? In other words, if in addition to the, the carrier beat note, there's some other megahertz signal that leaks in.
Yeah, absolutely. So so that depends on the frequencies where you have these peaks. Typically the PLL, so it's with a bandwidth in the kilohertz range. For example, if you have a peak Let's say at 30 megahertz, you don't care much because it's not where you are tracking or tracing the signals. So, but if it's very close to the carrier bit node or the clock side bump, so this may affect. There are some estimates on the harmonic distortion and requirements. I think on top of my head, it's minus 60 dBc, what it's acceptable by the instrument, but also depends on the interferometer. So it's less, let's say, sensitive for the scientific interferometer because of higher noise, but it's less let's say, critical for the test mass or for the reference ones. So we have requirements from external peaks in band that may come from Strilight, EMC coupling, or spurious peaks from the QPR. For the Phasemeter, it doesn't matter the procedence. What it matters is whether it's close or not to the signal to be traced.
Thank you. I think in the interest of time, let's thank our speaker again. Thank you, Esteban. And we now have our last speaker of the session, Davide Dal Bosco from Trento is going to talk about torsion pendulum improvements for small force measurements on the LISA test masses.
Yeah, so here is the LISA sensitivity. At low frequency, we are limited by true forcing acting on test mass. Instead, at higher frequency, we are limited by the measurement, interferometric measurement of the distance between the test masses. The GRS is the system responsible for for several stuff, but it's the one responsible for achieving this very stringent requirement on the stray acceleration of the test masses. And yeah, the test mass can be tested in two ways. By making a dedicated space mission like LISA Pathfinder, which we also, it was a huge success and demonstrated that this technology is ready. But it can be also tested on ground with torsion pendulums. And this is what I will focus on this talk. At the University of Trento, we have two torsion pendulums for the testing of the LISA GRS. The single test mass torsion pendulum, which is displayed here. Here. In this case, the test mass is suspended by its center of mass. It's a very sensitive torsion pendulum, but as you can imagine, it's only sensitive to forces that produce a torque on the test masses. The second torsion pendulum is the 4 test mass torsion pendulum. In this case, the cross-shaped inertial member makes so that the test mass is not mounted directly under the suspension point, but is mounted off-center. The arm length is about 10 centimeters, and it's sensitive also directly to the forces acting on the test mass, which makes it more similar to the true LISA configuration. The GRS subsystem testing is with torsion pendulum is very important because it's the only chance that we have to measure on ground the forces acting on a hollow test mass in LISA GRS, and it encompasses several tests. Here I show you some of the tests that we can do. For example, we test the performance of the capacitive sensor in terms of sensing actuation, noise, and calibration. We can measure thermal effects. We can measure the surface properties of the test mass and the electrode housing in terms of, like, for example, photoelectric yield, patch potential, and so on. Then we can also measure and place an upper limit on the overall force noise on the test mass. Then we can measure also stiffness and also other stuff. And very importantly, we can also make a full discharge test in which we discharge the test mass with the pulse illumination synchronized with the potential produced by the front-end electronics. I also list some of the hardware, the most important hardware that will be tested in Trento, and that's it, the engineering model of the electrode housing produced by OHB Italy, then a version of the front-end electronics, which is provided by Thales Alenia Space Switzerland and ATHZ. And then we also have a TRL6 version of this charge management device which has been provided by University of Florida, FiberTech, and NASA. And then we also we are procuring and designing new hollow test masses, which will be representative of the LISA one in terms not only of geometry, but also material, coating materials and finishing. In the next slide, I will focus on the single test mass torsion pendulum, which will be for the first time a part of the testing campaign on ground. The single test mass torsion pendulum is very, very sensitive, but as I mentioned before, sensitive to effects that produce a torque. And this makes it ideal for measuring, for example, disturbances coming from the electrodes and, for example, from the front-end electronics. We are also planning to improve its sensitivity on this effect by reducing the test mass to electrode dowsing gaps by mounting a bigger test mass. We are also envisioning to use it for dedicated tests on gas burst, more known as glitches that were observed in LISA Pathfinder. Here I also explain some of the measurement that we can do more in detail. For example, a very important measurement that was conducted by Vittorio Chiavegato, a former PhD student of our group, is to measure the noise related to uncorrelated gains in the actuator, in the front-end electronics. So, for example, imagine that we have some potential applied to two of the electrodes, and the amplitude, nominal amplitude of this potential is the same. But there is a fluctuation in this potential due to random and uncorrelated variation of the gain of the front-end electronics on the two electrodes. As the two electrodes are mounted with a given arm, they produce a torque noise. This torque noise was observed on the torsion pendulum for a few values of the commanded voltage. Other tests that we can do with the single test mass torsion pendulum include also actuation nonlinearities of the DAC and test of the charging of the test mass. More particularly, since it's very sensitive, it's very good to make a measurement of the continuous discharge, so the random fluctuation of the test mass charge while illuminating it for a long time due to the random transfer of charges between the test mass and the electrode dowsing during illumination. And here you can see some of the data that was acquired on the single mass torsion pendulum compared to the four test mass torsion pendulum. These measurements are easier on the single test mass torsion pendulum because it's more sensitive, so they last a shorter amount of time and they are very, very good quality. Then we move to explaining a little bit the four test mass torsion pendulum. The four test mass torsion pendulum is the main facility for the GRS force noise testing. The aim when they build this torsion pendulum is to reproduce the environment around the test mass in the most representative way possible. So all the hardware has been, it's as representative of the LISA hardware as possible. You can see here the force sensitivity, force noise on the four test mass torsion pendulum. Of course, on ground we cannot reach the sensitivity for LISA and so on, of course, but the sensitivity that we have right now allows us to measure forces of 10 femtometer with an inclination time of 1 hour in a 2 millihertz frequency. So still we can test and measure some of the critical parameters with a very, very high level of accuracy. You can see here the inertial member with the four test masses mounted on a cross shape. And here you can see one of the test masses, which is on the exterior identical of the LISA test masses in the flight model replica of the LISA Pathfinder electrode dowsing. Here I list some of the upgrades that are being that we have been doing for adapting the 4 test mass torsion pendulum to the testing campaign of LISA. And some of these are work in progress, others are completed. Most importantly, we will receive in the future the engineering model of the new LISA electrode housing provided by OHB Italy. We will machine and coat new hollow test masses with a coating which is representative of the one of LISA. We will receive, probably at the end of this year, a copy, an elegant breadboard model of the LISA front-end electronics. And we received last year, in June 2025, the TRL-6 charge management device by the University of Florida and FiberTech, together with its multi-core fiber, which will be the same in LISA. I will spend the last minutes of my talk by giving you updates on the upgrade that we have been doing this spring, that is substituting the old tungsten fiber of the torsion pendulum with a new silica fiber. The silica fiber has been manufactured at the University of Urbino with a machine that makes this fiber for Virgo. So you can see here a video of the pulling of one of the fiber. We start from a piece of silica, we heat it up with a laser, and then we pull the ends of this silica stick to produce a very, very thin fiber. This fiber is 80 micron in diameter. Silica has better mechanical qualities than tungsten and should grant a lower level of thermal noise and a higher quality factor of the torsion pendulum of the oscillator. Here also you can see the data that we acquired with the silica fiber compared with the thermal noise and the LISA sensitivity. Since, as you can, in the picture before, you can see that we are very far away from the thermal noise of silica fiber, but we also were not limited by the thermal noise of tungsten fiber. So I will explain one of the main reasons why we decided to substitute the tungsten fiber with the silica fiber, and that's it for solving a low frequency drift of the equilibrium point of the torsion pendulum, which is called within our group with the term unwinding. In dark blue, in this picture here, you can see the evolution of the oscillation of the torsion of the 4 test mass torsion pendulum. You can see that there is a linear drift under it. In light blue, there is a time series of the single test mass torsion pendulum, which employs since several years a silica fiber. You can see that this drift is basically zero. So installing a silica fiber, we hope to also achieve like a very, very, very low drift in the equilibrium point. The drift of the equilibrium point of torsion pendulum is not ideal for several reasons. Of course, like we heard this morning about stiffness and stiffness terms. So anytime there is like a drift of the position of the test mass within the sensor, there is a force, a spring-like force. And if this drift is somewhat noisy, also the force is noisy. So not having this drift helps us hopefully to reduce these stiffness-induced noise sources. Secondly, one thing that was a problem for us during the continuous discharge testing campaign is that we observed a correlation of the equilibrium potential of the test mass during an illumination with the position of the test mass within the electrode housing. And you can see here from the data on the y-axis there is the X position of the test mass in the electrode housing, and on the Y the equilibrium potential during an illumination with nominally the same illumination pattern. You can see that there is a very, very clear correlation. So if the test mass is drifted noisily inside the sensor, we also observe like that the potential of the test masses evolves with time. And once we take the spectra of the time series of the potential of the test mass, we have extra noise due not to the charge transfer itself, instead by this change in the equilibrium, due not to the charge management system itself, but the position of the test mass within the sensor. And in some cases, this was a limiting factor in our setup, and we had to subtract this effect from the data. But if we can achieve no drift of the test mass position inside the sensor, we hopefully don't have this noise source. The data show that here in this plot here, I show two of the runs that we have with the silica fiber recently, and the amount of unwinding, so the slope of this drift over time. After suspending the pendulum, this drift is very strong, but it decreases with time. And also the second run, so after suspending the pendulum again, we observe this drift gets lower with time. If we extrapolate this data, we think that we can achieve a lower unwinding rate than the tungsten fiber within around 10 days. So we hopefully get to this level by just waiting and having the fiber to settle and to stabilize. Lastly, I would like to speak about what is the measuring quality factor of our torsion pendulum. We measure the quality factor from the damping factor of the harmonic oscillator. Here is the equation, Newton equation of the harmonic oscillator. Here the beta factor is related to damping, and it's related to the quality factor Q by this equation, where E is the moment of inertia and T0 is the period of the oscillation. By conducting some measurement, we observe a linear dependence of the beta factor on pressure. So right now we are limited not by the intrinsic damping of the fiber, but by the residual gas damping in the vacuum chamber. We are sitting now at around 10 to the minus 6 millibar. So with time also, we hope to go to a lower pressure and not be limited anymore by the residual gas damping, but by the quality factor of the fiber. If this is the case, we estimate the quality factor of the oscillator of the torsion pendulum to reach a value of 500,000. Finally, here I show you again the amplitude spectral density of the force noise on the torsion pendulum in the case of the tungsten fiber in red and of the silica fiber in blue. We observe that at high frequency, right now we have an excess of readout noise that we are investigating, and we hopefully can reach back again the level of the red curve. At low frequency, the silica fiber shows a very good noise, and so that's good news. We will track the evolution of noise and the unwinding over time, trying to figure out what limits the performance of silica fiber. Okay, that's it. So yeah, thank you so much for the attention.
Yeah, thank you, Davide. I would like to suggest that if you have questions for Davide, we take it in the coffee break so that we can at least have 15 minutes of coffee break. Let's thank all of the speakers again. Sorry for running a little bit late. Enjoy the break.